Hello, everyone. We're going to go ahead and get started. We'll probably have some people coming in as we start here, but I'm Greg Larson with the Seiler tech support team, and our webinar today is selecting the right GNSS correction for the job. It's a topic we get a ton of questions on, so we brought in a special guest today. Jason Evans joins us from Trimble. He is the current portfolio manager for the real-time corrections division at Trimble. And Jason comes to us with over 2 decades of experience in the geospatial and survey industry, both as a professional land surveyor and as a subject matter expert in optical, scanning, photogrammetry, GNSS, and GNSS correction technologies. So I will give it over to Jason.
Great, thanks, Greg. Hopefully everyone can hear me just fine. We've got an absolute ton of material to get through today. We've been trying to do this webinar presentation to really help get the word out in conjunction with some programs that we've got going on to introduce everyone out there to Trimble RTX correction technology. And we felt like this was a terrific opportunity to go through and talk about a lot of the stuff that we deal with on a day-to-day basis in terms of the corrections that we need to have accurate positions out there in our real-time workflows with our GNSS receivers. So this is our agenda today. There's an absolute ton of material to get through. We spent some time talking about the biases in GNSS measurements, mainly so that we all have a really common vocabulary and understanding of what it is that we're trying to correct. And then we look at actually how those corrections are applied through various positioning processes. Working with Greg, on the local front, we want to talk about all the correction products that are available in your areas. So we've got the section on Trimble GNSS corrections, and then we go through and we make some value propositions to you about why this is important to you, especially now with solar cycle 25 approaching, and all the practical considerations that you need to make in terms of actually thinking about your choice of GNSS correction and GNSS workflow that you're going to follow. So again, it's a ton of information, so I've got to move pretty quickly to get through it all in an hour. The way that I like to start talking about GNSS corrections is actually to start by talking about total stations. So I feel like there's a lot of folks that are probably familiar with how a total station works, and a lot of the principles that apply to how the total station works are the exact same principles that we're using to range to a GNSS satellite that's orbiting out in space. So I think it helps to start from a frame of reference that maybe we all understand. And so in this case, showing on the screen, we have someone using a robotic total station. They're using the EDM to measure, right? So that's the electronic distance measurement portion of the robotic total station. That part of the total station creates a laser beam, right? A wave of light that goes out, strikes a target, strikes a surface, and reflects back to the total station, right? And we know that that is obviously moving at the speed of light. We know what the speed of light is in a vacuum, right? And we know that we can actually make some corrections on the calculation for the speed of light by setting an accurate temperature and an accurate pressure inside of our total station. And the way that this works is the light goes out, strikes that target, and comes back moving at the speed of light. So we divide by 2, right? That's simple thing to understand, just because the light had to go out and had to make the return trip, right? So it made the trip twice instead of just once. So when we use this beam of light, we set various wavelengths, right? So that we can measure and we can start figuring out the units of distance that represent the range out to our target. And we're doing a really similar thing with a GNSS satellite, right? We're sending out a signal. We don't necessarily think of it as a beam of light like you might with the total station, but nonetheless, it's still just another wave that is coming down to us out of the satellite, and we can use it to establish range. Right now, inside the total station, we can actually do some clever things by doing analysis on this wave of light as it returns. So we can check the phase, we can set it through SAW filters and things like that to get those really fine measurements. And likewise, on the GNSS receiver that you have, we're also doing these very fine measurements. So when we talk about carrier phase ranging, what we're really talking about is analyzing that carrier wave and trying to figure out those very, very small bits of the measurements so that we get an accurate range out to the GNSS satellite in space. Now, very similar to a total station workflow where you might do a resection or something along those lines to figure out your position, we're doing a very similar thing with the GNSS satellites. So if we can calculate our range to several GNSS satellites all at once, then we can start figuring out our position very accurately on the planet. Right now, just like our total station, though, that's not without some sort of errors or biases that we need to mitigate. So just like in your total station, when you're setting your temperature, when you're setting your pressure, you're mitigating those biases in your measurement, right? Hopefully everyone's doing that on a day-to-day basis, especially if you're out there trying to do really precise work, setting control or something along those lines. So with our GNSS receiver, we do some similar things. So let's take a look at the signals first, and then we'll talk about the biases after that and see what we're adjusting on the GNSS side. So I'm guessing that probably everyone has seen a very similar slide to this. This really hasn't changed very much in the last 30 years plus, probably longer. For GNSS positioning. So the signals really haven't changed very much, right? There's more of them, and we're putting more information on them, but fundamentally they all function the same way. So if I start down at the bottom of this page, we've got a carrier wave, right? Just a graphic to represent this wave. This is being generated by the atomic clocks that are inside the satellite, right? So the atomic clock creates this wave, and then it encodes information onto this wave. So the easiest way to think about this is just like when you're listening to the radio, you tune your radio to 105.7 FM, you're listening at that carrier wave frequency. And of course, encoded on that carrier wave are all the songs, all the DJs' voices, the talk radio, whatever it is you're listening to, right? So they're putting information on that carrier wave, and the same exact thing is happening with a GNSS carrier wave, right? But instead of it being voices and music, it's unfortunately just a whole bunch of data. Probably wouldn't be very fun to listen to. The data, if we start back at the top of this screen now, really comes down to these codes, right? So every single GNSS satellite is given what they refer to as a PRN, which is its code, and it simply repeats that code for its entire life over and over and over again in these CA and P code messages, right? So this is a giant string, letters and numbers that are coming down. They're very important, though, to our position because we can use the code to actually calculate a range to the satellite, just like we can also use that carrier wave at the bottom to calculate the range. So starting at the top, the CA code, this is referred to as the coarse acquisition code, right? So this is coarse as in not fine, right? So think of a coarse saw versus a fine saw. That's what we're talking about when we're talking about the CA code. The reason that this one existed, at least in the beginning, was back in the 70s and 80s, you didn't have the processing power that you have today. So they had to create a code that was easier for the computing power to match, right? To create a duplicate, figure out where it was, and then apply that to the P code, right? So the CA, coarse acquisition, helps you acquire the P code. Now the P code is the precise code, right? So the precise code is much more dense, a lot more information. And if you notice, you can see the modulation there at 1.023 megahertz for the CA code and 10.23 megahertz for the P code. So there's literally an order of magnitude difference between those two. And that was a pretty clever thing, not only to save on computing power, but also because anything that's impacting your ability to track the CA code should be impacted at an order of magnitude greater when you're trying to track the P code, right? So that was a very clever engineering design that the folks that made these first systems came up with. And it's something that we can actually use to help give you very precise positions out there on the planet, all right? So that's the CA code and the P code. Now that's the information that is encoded on that carrier wave. Now, when it comes to the carrier waves, remember that there's a number of them, right? What I'm showing here down at the bottom is the L1 code. That's the frequency of the L1 code for the GPS satellite system. But keep in mind, of course, there's other codes that are out there. There's L2, there's L5, there's all these different constellations like GLONASS and Galileo and Baidu, and they might slightly change how they refer to these codes, like Galileo E6 instead of calling it L6, right? But these are all codes that are in the same space, in the same radio frequency spectrum, between 1 and 2 gigahertz. That is referred to as the L band, right? So the nav message, not to leave that one out, the nav message is also very important to us. It has all the precise ephemeris information and the satellite health and information like that included on it. So that means that whoever is running that constellation of satellites, so in the case of GPS, for instance, it would be the United States Department of Defense, or if it was the Galileo satellites, it would be the European Space Agency. They have a ground control segment, and they're constantly monitoring for the position of these satellites, and they're constantly sending information up to the satellites to modify that nav message, right? To update the ephemeris, to let you know if the satellite is healthy or unhealthy or anything along those lines. So the nav message is becoming pretty important to us. It's a terrific thing to be able to use for anti-spoofing. And of course, nowadays, with a lot more bad actors out there in the world, spoofing has become a real challenge and something that you might have to deal with at some point in your geodetic surveying career when you're using GNSS. Okay, so that's the signals, but then we have to really talk about the biases, right? So all of these biases exist out on any range that we try to calculate to a satellite. There's a number of biases, a number of which we're correcting, and some of them we can't actually correct for. And so on this particular screen, I show the example of a formula for a pseudo range calculation to a satellite, right? And every single one of those variables, we're going to step through those and see what those variables are and how they might be impacting our calculation of that range. Now, the first section that I'd like to pay attention to is actually covered there in orange brackets and is labeled URE, and that is the user range error, okay? And that has to do with the clocks, the orbits, and the atmospheric parameters that we are actually correcting with a corrections product. So all of those ones in the bracket, handily enough, are the same things that are in our correction products. So we're going to take a close look at those and see how they might impact the measurements. This very first one that we'll start with, this has to do, hopefully you can see my mouse, with these DT portions of it. So these are the differences in time, right? And there are two components to the time that we have to worry about. The first being the time that exists on the satellite clock, right? And then the second is the time that exists on the receiver clock. So when we were talking about the total station and we talked about that laser beam going out and coming back, inside the total station, there's a copy of that light beam, right? A copy of that wave that is created. And inside the total station, they're able to do a comparison of those two things. We do the same exact thing with a GNSS receiver, right? So we know what the wave should be for an L1 signal coming out of a GPS satellite. So we make a copy of it inside the receiver, right? So what the wave should be is, of course, determined by the atomic clock that is on the satellite. So those atomic clocks keep very, very precise time, right? So they're typically like a rubidium atomic clock or cesium atomic clock, and they keep accurate time out to the billionths of a second, right? The nanosecond mark. And if you're wondering, the C, of course, in this equation here is the speed of light. And so if we're thinking about the speed of light and we're thinking about nanoseconds, in about 1 nanosecond at the speed of light, you travel roughly 1 foot. So that says in 3 nanoseconds or 3 billionths of a second, you have lost a meter of range or introduced a meter of range error if you're even down to 3 nanoseconds off. So it's pretty incredible how closely we have to be able to track the time from these satellites, right? That becomes a very important component of our errors, all right? The atomic clock, its job is to work as the oscillator, right? To create that carrier wave, to get everything encoded on that carrier wave and send it down. Every single constellation that's out there has to use its own time system, unfortunately, because you have a different ground control network, right? So time here in the US that they're calculating at the DoD is not the same exact time system that they're using at the European Space Agency, right? So these are different time systems, and we actually have to correlate all that information within your receiver to not lose those little nanoseconds and introduce errors. And I think I've got some slides ahead that show the actual what that looks like, the calculation inside the receiver. And of course, the second one is that receiver clock, right? So inside the receiver where we need to make that copy, we also have to depend on an oscillator, right? Because we have to make a copy of that wave to compare the two waves to. So inside the receiver is not an atomic clock, because that would make a receiver entirely too expensive, but there's actually a quartz crystal clock. And that's very similar to what you might think about as the clock that's inside your wristwatch, right? It's a quartz crystal clock. But in the case of your GNSS receiver, it's actually a little bit more robust than that. It's what's referred to as a temperature-controlled quartz crystal oscillator, right? So the temperature-controlled portion mitigates the impact of temperature change on that clock. So in other words, that clock is still able to keep really accurate time, even though throughout your day the temperature might change, which can cause some expansion on the quartz crystal that's contained inside that element. So just something really important to think about when you're looking at your GNSS receiver spec sheet. Of course, it has a temperature range that you're allowed to work within, and that temperature range is there. Obviously, it's not just because your batteries go dead faster when it's cold out, but it's also because we need to be able to change that oscillator, and we need to be able to mitigate the impact of the temperature change on the oscillation to create that copy of the wave. Right, so those are the first two sections of our formula here: the atomic clocks that are out there in the satellite in space, and the receiver clock that's in your receiver on the ground, making a copy of those waves. All right. The second parameter of that formula is DP, right? And this is the actual position of the orbiting satellite out in space. So in this case, we're trying to show an example of where the satellite thought it was going to be, right? Where it planned to be, and that's the information that's contained in the ephemeris of your nav message, right? And then where the satellite actually is, right? So these satellites that are out in space, they're constantly being tugged around out there and buffeted around in space. And the way to think about this, of course, is that they have a lot of gravitational forces that are impacting them. So the gravity of the Earth, of course, is pulling them around. The gravity of the tides, as the tides change, of course, will pull these satellites out of orbit, right? The gravity influence from the moon will move the satellites out of orbit. And then, of course, the sun itself, especially as the sun is releasing particles, out into space, those charged particles are hitting this satellite. Right now, think about these satellites. They've got these giant solar arrays on the side of them, and those solar arrays can actually act like sails. So just like on a sailboat where the wind is pushing the sails, all those charged particles that are coming out from the sun can actually strike against the satellite, and there again cause its orbit to be perturbed. So if you're not correcting for that, you're failing to mitigate a large source of error in your range estimations to the satellites, right? So just something to keep in mind as well. Here's our clocks. So this one shows the master system clock offsets that you might see to the various constellations that are out there. So here again, you can see that we're measuring in nanoseconds, and we're paying attention to the drift, over time. So this is nanoseconds per second that we're losing. And then again, the same exact thing on the receiver side. We're watching the receiver clock. We're looking at the GPS system in this particular case as our master clock system, and we're calculating the offsets within our receiver for that time frame. Right. So very important error components. Very important to mitigate these error components in order to have precise measurements on the ground. Now, if we look back to our formula, we're moving out now to the DI and DT area. So these are the differences in the ionosphere and the troposphere. And so we show a picture here on the screen of the Earth, and it shows both of those layers of our atmosphere. Now, I think I have the next slide ahead talks about the troposphere, so we'll focus here on the ionosphere. The ionosphere roughly extends from about 50 kilometers out to 1,000 kilometers above the planet. Now, the ionosphere, as its name implies, is this area of atmosphere above us that is loaded with ions, right? Loaded with charged particles. And this animated GIF on the screen, what it's showing is that these charged particles every day as the Earth rotates about its axis and the sun shines on a particular portion of our atmosphere, these charged particles get excited, right? And when they get excited, they start spitting out electrons. And those electrons, again, are a charged particle, right? So since they have a charge, they're attracted to the geomagnetic equator and to the poles of the Earth where there's additional charge, right? So what we're showing here in this GIF is what is referred to as the total electron content, right? So as the sun shines on a portion of the atmosphere, it excites it and more electrons are ejected from those ions. That increases the electron content of the atmosphere in that place. And as that increase occurs, it changes the density of the atmosphere, right? So as that carrier wave comes down from the GNSS satellite, travels through our atmosphere, right, hits our space, it's actually hitting different densities as it comes to us so we can pick it up at the receiver, right? Those different densities can actually perturb that wavefront, can cause deflection in the wavefront, can diffuse the wavefront, and can make it difficult for us to pick up that signal and have a good copy to compare to from space. So something very important to keep in mind is that this happens every day, right? The Earth continues to rotate on its axis, the sun continues to shine, and every day the atmosphere is excited. So when this gets worst, right, is right around 2 hours or so after noon, right? So at noon, of course, the sun is shining down on the atmosphere, it's heating everything up, and then over the next couple of hours, as that sun shines, the atmosphere gets the most heated, and that is when the most electrons escape, and that is when you have the greatest change in density, right? So this is something to keep in mind. We're going to talk solar cycle 25 later, but this is something that you can mitigate on a daily basis by simply avoiding those hours, right? If you can push your GNSS work to the beginning of the day, for instance, or later on in the evening, then you're going to have much more precise measurements. So just something to keep in mind. Again, we will talk about how we mitigate these things in the slides ahead. So troposphere, this is that area of the atmosphere that's very close to the Earth. The easiest way to think of the troposphere is this is where our weather happens, right? Now, for those of you who remember your Earth science class from high school, you notice that I skipped a whole bunch of sections of the atmosphere, right? The thermosphere and the mesosphere and all the other ones. They really don't have the impacts on GNSS measurements that the troposphere and the ionosphere have. So it's easier to kind of combine all those into just talking about these two. The troposphere, just like the ionosphere, has the ability to have density changes, right? If you think about a hurricane and the low pressure fronts that are associated with that, or if you think about a passing thunderstorm and how it's potentially, there's potential there that the front of that storm actually passes over your base station receiver before it passes out to your rover receiver. You can think of the different densities in atmosphere. And here again, that can cause changes on that carrier wave, right? And perturb the wavefront of that carrier wave and cause some dispersive effects. So this is referred to as a wet component because of the density in our atmosphere, right? And if, again, left unmitigated, it can contribute errors to our range measurement out to the satellite. So again, those are all part of what we refer to as the user range errors. Those are the orbits, the clocks, and the atmospheres. And those are the things that we're actually correcting when we talk about GNSS correction products. But you'll notice that out here at the end of the formula, there's still a few more variables to go through. So we'll go to the next slide and we'll talk about these two variables as well. I like to think of these as sort of unmitigated sources of error, right? Because these are things that we aren't necessarily fixing with a correction product, but these are the things that you're going to try to mitigate out in the field through best practices, right? So the first one is at the MP that is your multipath. Now, everyone is probably familiar with multipath, right? Multipath occurs when that carrier wave, the signal from the GNSS satellite, comes down and strikes an object like a reflective building or a windshield on a car or something like that, bounces off it, and then makes its way over to your GNSS receiver. Now, multipath can be pretty difficult for us to detect at the receiver. There are some techniques that we can use. For instance, there is a polarization to that actual carrier wave that is generated from the satellite. So because that polarization is right-handed, by the time that the carrier wave bounces off something, it should be reversed. So we can reject some of that information right at the antenna, right there at the receiver antenna. And we can do our best to begin mitigating that. However, we can't necessarily get rid of all of it, right? So if you're really out there and you're in one of these urban canyon environments or something where you've got no choice, you've got reflective buildings and everything is fighting you, you've either got to increase those occupation times, or you've got to look at your traditional survey tools like a total station, digital levels, things along those lines to get the work done. Right now, with Trimble ProPoint receivers, though, and with all the terrific engineering that has gone into Trimble receivers, we are able to mitigate a big chunk of this. So keep that in mind. Likewise, trees are a huge source of multipath. Anyone who's ever surveyed next to a tree or had to go under a tree, you know that can disrupt your GNSS signals. Here again, it's the same rules. You've either got to increase your occupation times, or you've got to make use of some of those offset functions that are built into your software so that you can still maintain productivity. Stand away from the tree a little bit, use the offset function, take your measure over to the tree, right? Again, ProPoint will do its best and will give you a terrific chance of getting good measurements in those areas, but you do have to watch out. Watch those precision error estimates that are displayed in your software, and if you see them creeping up, you know that you're pushing it a little bit too far. Right. The last variable that we've got here in our equation, this actually has to do with noise inside the receiver itself. So every single receiver, of course, has a very sensitive antenna that is built into it, right? Especially our smart receivers, obviously. Modular receivers, you got an external antenna, very sensitive again. But these receivers, they have sources of noise as well, right? You've got different boards inside the receiver, whether it's a cellular modem board, the main processor board for the receiver. Those generate noise inside the receiver themselves. Likewise, there's actually noise coming from outside the receiver, right? So this is interference from nearby radio, from nearby electrical sources or things along those lines that can actually impact the receiver's ability to get a clean signal, right? So this is something that you can't really watch out for, at least in terms of the receiver noise inside, but a lot of receivers now do have the ability to do a spectrum analysis and show you the receiver noise outside. And certainly if you ever send a T04 file into your to your Trimble support folks, that's exactly one of the things that they're looking at is, was there a lot of noise in this environment? Was someone either jamming, whether it was purposeful or whether it was accidentally, on the same frequency that we depend on to be able to track the GNSS signal? So again, not something you necessarily can watch out for. So you got to really depend on those precision error estimates to let you know if something bad is going on. All right. So hopefully that makes sense. These are our two formulas. Again, the one on the top is a pseudo range formula. This is using code. So that's that CA and P code to determine our estimation out to the satellite. And then the one below that is our carrier phase equation. So that is showing us how we would calculate an actual carrier phase solution out to the same satellite. Get enough of those satellites, get enough ranges to those satellites, and effectively you're doing a resection just like you are with a total station, right? Not magic. Nothing is magic here. It's all just physics. So when we begin talking about the actual positioning process itself, we can, again, I've got the same variables here on the screen, and we can talk about some techniques that we have in these various positioning processes to deal with these biases. So for right here, we can see the DT, so that is our satellite clock. And again, the DP, that's the position of the satellite in its orbit. Then we have our ionosphere and our troposphere, okay? Now, what I'm trying to show with this graphic is you've got two receivers. Maybe this was a static GNSS mission, or maybe this is base rover real-time kinematic. Either way, the important part of this is that you have two receivers simultaneously observing this satellite out in space. So if that is true, right, if we're simultaneously observing the satellite out in space, it's fair for us to get rid of any differences in the atomic clock. It's fair for us to say that the position of each would be influenced by how far out of orbit the satellite is, right? So we can begin to actually cancel out those biases in a differential RTK scenario or a static GNSS mission, right? Now, you'll notice that I've got listed on the bottom here baseline, and this becomes critical for these other two components, for the ionosphere and the troposphere, and the biases that they inject into our range. The baseline length is the important part when we think about real-time kinematic workflows. What is the difference, the distance between these two receivers? Because is it fair for us to say that the atmosphere is the same at my base as it is at my rover if my rover is 30 kilometers away? Probably not, right? So that baseline length becomes an important part of our consideration when we're choosing the tools that we work with. In this case, the baseline length, if you look at your GNSS receiver spec sheet, is there's an error that's listed there, and it tells you that the accuracy of this receiver in a real-time kinematic workflow is, let's say, 1 centimeter plus 1 part per million. Well, that 1 part per million speaks directly to that baseline component. So at 1 part per million, that means that the further away your rover is from your base, or the further away your two static receivers are, the greater chance you have of having differences in your atmosphere and therefore greater error. And the easiest way to think about it is 1 part per million. That is 1 millimeter per kilometer that you go away from your base station, right? So keep that in mind. If you're working 10 kilometers away from your base station, you're including another centimeter of error in your measurements. Now, the antenna phase center, that's already got a centimeter of error, right? That was that first part, 1 centimeter plus 1 part per million. So when you're thinking about your measurements, you could have up to 2 centimeters of error at a 10 kilometer long baseline. So keep those baselines short is the moral of this story, right? Now, if we expand on this and we start thinking about adding in a second satellite and second signals in the same scenario, here again, we can begin to cancel out more of the variables, right? So in this case, again, you see the time at the satellites, the position of the satellites, impact of ionosphere and troposphere. But here, since we're observing two satellites simultaneously from two separate receivers, and we have a second signal coming into us on both of those receivers, we can actually begin to cancel the receiver clock errors. All right. So this is why differential RTK and those really short baselines works out so well, because we're actually able to mitigate almost entirely these biases. Right. So that is a reason why this is the tried and true workflow that all of us go to, which is terrific if you can have a site base. Right. But something to keep in mind is that you can't always be in that position where you have a site base. Right. And something else to keep in mind is that comes at a cost. Right. So if you want to have a site base, that means you got to have control. Right. Or at least you've got to do post processing on a here location at some point in order to establish a coordinate for that base station. That comes at a cost. It takes time, right? It takes time to set up the second receiver as your base. It takes time to set up that external radio, hook up the battery, everything else. It's a more complicated workflow. Now, one thing that's really important to keep in mind about this workflow is that you also have to have the same satellites visible at your base that you do at your rover, right? You can't cancel these out if you don't have the simultaneous observation. So that is to say that if your base is GPS GLONASS only, and you've got a rover that's multi-frequency, right? It's picking up GPS, GLONASS, Baidu, Galileo. You're not correcting any of those Baidu or Galileo satellites if your base is GPS GLONASS only. So make sure that when you're thinking about purchasing or you're budgeting for your purchase, you are thinking about having these in a matched pair, because it doesn't do you any good to have signals on one that are not available on the other. Right, and that the same thing applies in real-time networks, and we'll talk about that in a couple of slides. So just one other note that I like to make here on this slide is that as part of a base rover workflow, please make sure that you're out there and you're getting your radio frequency that you're broadcasting on licensed. Work with your partners at Seiler, make sure that this is in place. The fees that can be levied against you from the FCC are pretty exorbitant when it comes to operating what they refer to as a pirate radio station. Right, so the fees are somewhere in the range of up to $100,000 a day. Now, most people that I've talked to that have gotten caught, gotten fined, they haven't had to pay $100,000 a day, but that's a pretty steep fine. The other thing that the FCC will do in this situation is they'll find out how long you've been on a particular job site, and they'll give you that fine for every single day that you've been there. So if you've been working there for three months or something like that, they will hand you 90 fines up to $100,000 a day. Can get quite expensive. So please make sure that you're not being a pirate broadcaster. If you're using a UHF or VHF radio and you're in the United States, you got to get that licensed and you got to encode your call sign into the radio and do all the things that they say you have to do. Okay, that's my soapbox on base rover, licensing your radio. Now, when we're thinking about a real-time network, you'll notice that it's a very similar concept. In fact, it's a differential solution, just like base rover RTK. In this case, the difference is that we have a whole bunch of reference stations around an area that are providing us with a view, that's providing us with the state of space above us. Right, so all of these reference stations simultaneously doing the things that our base was doing in the previous couple of slides. They're taking all that information, sending it back to some sort of processing software. That processing software makes a correction for the clocks, for the orbits, and makes models for the atmosphere, for the ionosphere, troposphere, and takes that information and makes it available to you via the internet, right? Typically via cellular internet. So again, no real magic here. And then when we're talking about a precise point positioning solution or PPP solution like Trimble RTX, it's the same scenario. So we've got a global reference station network in this case. We're tracking simultaneously the state of space above us. We're calculating all the clock offsets, the orbits, and we're creating models for the atmosphere. And in the case of Trimble RTX, we're using geostationary satellites to send that information back down to you on the ground to improve your positioning. Right now, this information is also available to you over the internet. So if for some reason you were unable to track at some given time the RTX satellite, you could switch to an internet type correction source and get the same corrections coming down to you via PPP. Now, Trimble RTX, unlike those differential workflows that we were looking at, PPP technologies are not a differential workflow, right? We are modeling out all those ambiguities so that we have a precise measurement. So when we're talking about PPP, there's usually something that we refer to as the convergence time, right? So that is the amount of time that it takes to get those models to us and to start resolving the ambiguities of the clocks and the orbits and the atmospheres so that we end up with a precise position. All right, PPP technology has been around for quite some time. Trimble RTX, I think, is well over a decade old now. Real-time network technologies have been around for even longer. Trimble VRS networks, of course, have been around for over 2 decades. And I think we're going to talk about all your local networks now. I'll turn it over to Greg because he's got the real knowledge on the ground. And Greg, if you could speak to the networks in your area, that'd be terrific.
Yeah, so we've got a number of choices in the Seiler areas that we cover, and it's really more or less sectioned off by state, with the exception of in Indiana, Illinois, and then to a lesser degree in Iowa and Nebraska, we have a Trimble VRS Now network, and that's managed by Trimble with cooperation with some of the DOTs in those states, but. Currently, in most areas, you're getting all the 4 main constellations, and there's also an upgrade program in Illinois because some of the bases there are a little bit older. But if you're not seeing all 4 constellations in those areas, make sure you're on the advanced mount points that you see at the end of the list there. But that's kind of the gist in the Indiana and Illinois areas. If we can move on to the next slide. In Nebraska, there is an alternative since the VRS Now network is a little bit less dense. This network is there's talks on upgrading this network because it is GPS and GLONASS only right now. But But again, those are the CMRX and RTCM mount points that you should be using if you're on that network. So it's an alternative network in Nebraska, since the VRS now hasn't expanded fully into Nebraska yet, but that's kind of the rundown for Nebraska there. If we can move on to the next slide here. Missouri does have a dense network. It is run by the Missouri DOT. It's a Trimble network, but it uses the same technology as the Trimble VRS Now networks. It is a free network with sign up, and Galileo and Beidou were recently added in the spring. So if you're not seeing those satellites, make sure you are on the advanced mount points that you see, the RTX CMRX mount points and the RTCM 34 mount points. But very reliable network, much like I believe the Wisconsin. Oh, sorry, the Kentucky network is next. Sorry, in the picture there, I kind of grabbed the picture of that network, the sensor network there. I think it was the day after one of the hurricanes. So if you see a couple of red spots there, that's probably why. Just kind of a point on that. If you go to the VRS Now or the Kentucky Corps websites and you want to look at sensor status, that's kind of the color code that you see there. Green is good. Yellow, there might be a little bit of an issue there. Red is sensor. It looks like the base is out. But those have since returned after the time has passed since those storms hit that area. Run by the Kentucky Transportation Commission. Again, it's free with sign up, and same technology as the Trimble VRS Now technology. Has all of the main constellations, and again, those are the advanced mount points there. So again, if you're not seeing like Galileo and Beidou in particular, make sure you are on those mount points. The same story goes with Wisconsin. Again, very dense network, very good coverage in this state, run by WISDOT. Has all the main constellations. So if you're not seeing them, make sure you're on those two mount points there. We can, just contact us and we can check all your settings remotely in a lot of cases. And then as we move on to basically Iowa and Michigan in particular, there's other networks that cover that. They're run by the state DOTs in Iowa, Indiana, and Michigan. We've had good luck with those. Not many issues there. I think Indiana just recently upgraded to Galileo and Beidou, so get in touch with them or contact us if you need to get the settings for that. As far as Kansas goes, that's a really tough state to find a good RTK network in for some reason. So there's not a free public network. There's various agricultural networks, but it's kind of a mishmash of networks in Kansas. So, that might be a good opportunity, to try out something like RTX or something like that. So,
sure.
Yeah,
I think, in my experience, I live up in the Northeast. I'm in Pennsylvania. Some of these state agencies, they struggle to necessarily get the funding that they need, to maintain these networks, to get the newer sensors and the newest signals available to you. That's just comes with the territory, I suppose. So these networks that we are paying for, of course, our dollars, our subscription dollars, go directly towards the maintenance, the upgrades of those networks, and of course, pays for those network operation engineers that work 24/7 to try to keep those networks up and to address any station outages and things along those lines. So, I know sometimes when you have a free network available to you, it's really tempting to go out, hop on that network, but you lose a few of those things. It sounds like you guys have some pretty good coverage in your area, though. At least you've got multi-frequency. Where I am, all the closest base stations to me are unfortunately GPS GLONASS only. So, varies by where you are. So Centerpoint RTX, again, this is the PPP solution. Really, what we want to look at when we're talking about Centerpoint RTX is the fact that we've started including it on so many of your receivers. You guys should be seeing it now out there in the field, and it should be popping up as an icon when you're out there surveying. So again, PPP solution, global network of reference stations. That same professional network engineering team is making sure that this stuff stays up all day, every day, and they're doing their best to address any station outages and make sure that we're getting terrific data. So a lot of times when we were thinking about PVP technology or Trimble RTX, folks were just picturing those people who had to work out in the middle of nowhere. Maybe they didn't have cellular service, and hey, Trimble RTX was there available to you via satellite, so it was a great solution. But Trimble RTX, of course, is available to you via cellular and satellite. So there's no reason not to have this turned on in your receiver. Again, it's got the correction products that are going to help you maintain a very good position on the ground. Also, something to think about is that the added complexities that we talked about in a base rover workflow, you don't always need those added complexities, right? You don't always need a site base, right? So in one of those situations, you might want to be thinking about, is there a network solution available to me? Is there a PVP solution like Trimble RTX available to me, so that I can either A, use both my receivers as rovers, or B, avoid having to spend the time of setting up that base. So how it works, you've got a global network of reference stations. All right. Everyone always asks me how many reference stations there are. There's thousands. There's thousands in the U.S. alone. On top of the thousands that are already there in the U.S., there's actually dedicated groups within those or outside of those thousands that are actually used for separate functions like RTX integrity monitoring to make sure that the solution that we're sending out is really precise. Right, so there's hundreds of receivers that work on that. There's hundreds of reference stations that also contribute to our global ionospheric models, right, all around the planet. So plenty of reference stations that are out there. Most of these are Trimble alloys, right? So that means, of course, they've got GPS, GLONASS, BeiDou, Galileo. Everything is available to them. Every signal is available to them, and they're able to send that over to the server software. All those calculations are made for the biases, and the information is then sent out again over IP or via satellite and down to you on the ground. This is just some examples of what this looks like. So we talked about orbit bias, we talked about clock bias. So if we're tracking those inside the server software, the orbit bias on the top, you can see that it's that sometimes there's outliers, right? Sometimes the satellite gets really perturbed, and we're able to track that, and we're able to mitigate that, right? And you can see that the magnitude of those errors too is somewhere, some of them are almost out to 40 centimeters. So it could be a pretty big error if it was left unmitigated. Then down below, you see a plot of the clock biases. So the clock biases, you notice that there's a lot more variability there, right? They're kind of all over the place as we're getting these signals. So this is something where we actually have to correct it at a much faster cadence to make sure that you maintain a precise position out there on the ground. Remember, those nanoseconds matter, right? Those nanoseconds are feet of differences. These are some examples of the atmospheric modeling that's going on inside the RTX server. This just happens to be the ionospheric model over South America and the tropospheric model over Europe at some given point in time when I took these screenshots. So here again, we're seeing the density of electrons, we're seeing the tech count, and we're seeing how that gets modeled out. And then over on the tropospheric side, we can see the delay that's being caused by that sort of wet component of our atmosphere, right? And so we can send that model per satellite, per signal down to your receiver, and we can correct for it. So if you're kind of new to CenterPoint RTX, a lot of the reason that we want to talk about this was that we've started doing these activations of CenterPoint RTX on your equipment. I think, Greg, did you want to talk about this for what this means for Seiler customers?
Sure, yeah. So beginning April 1st of this year, if you purchase one of the receivers you see listed there, yes, we do activate the RTX for 1 year. It's not something you have to do. So when you get that or have gotten it, the RTX is active. So, and then for those, there's something at the end for those of you that already have receivers that you can sign up for. But yeah, it's these models here, and it's active when you get it. So I think we'll talk about how it works in Trimble Access here in a couple of slides. So
yeah, there we go.
There it is. So yeah, really the main difference in access is we have to, in the rover options, if you set up a survey style before, is to change that broadcast format to RTX SV, which is the signal direct from the satellite. So the SV is equivalent to satellite. So I'm guessing that's just kind of short for what that is. There is an RTX internet option there as well. So if you want to receive those corrections over the internet, that there's that broadcast format in there as well. So, but this is the main thing you need to change. And in Access 2024, this survey, there's an RTX SV survey style in there as well. So.
Nice. All right, thank you. Yeah, so again, these are probably icons that are showing up on your screen or survey styles that maybe you've had a chance to set up. And so practically, what does this mean to you, right? When you're out there in the field, you've got a job to do. You've got to choose the best job, the best approach. So I think we've articulated the value to some degree of making sure you've got multi-constellation, but and we talked about baselines and baseline lengths and keeping those short. And this table just kind of gives us some food for thought. So if I am utilizing any of these various solutions in order to have corrected precise GNSS, where does that get me to? And here we're talking about RMS, right? So this is a root mean square error. This means that we're a measure of accuracy, right? How far are we off from truth? Right, and we're saying for all of these, we're able to achieve 2 centimeters and 3 centimeters. And in our example, if you notice that there's some small text down there at the bottom, we show you how we got there, right? So for a real-time network, you still have to think about your baseline length to the nearest physical base station, right? So that adds 0.5 millimeter of error, right? It's not 1 part per million, but 0.5 part per million of error in the case of a VRS now network or a VRS network in general to your solution, right? So if you've got 25-kilometer spacing, nice dense network, or sorry, 50-kilometer spacing on a nice dense network, and you're standing right in the middle of them, you've got 25 kilometers to the nearest physical base. And you actually have to do the calculation here. At 20 kilometers, you would be at 2 and 3 centimeters. Again, when we're talking about a differential-based rover solution, example here was given at 10 kilometers. I think we talked about this one already. When we go 10 kilometers, 1 part per million, that adds 1 centimeter of error to our measurement and brings us to that 2 and 3 centimeters. Right, so this is something we definitely have to keep in mind when we're thinking about how we're approaching this. And I've got a couple of slides that show what this looks like, scatter plots and line plots, but they change, right? So I'm no longer speaking in RMS, I'm switching to the sigmas, right? And so I just want to make sure that everyone is aware that there is a slight difference between these two. RMS is a measure of accuracy, right? And the sigmas are a precision estimate, right? So one says how close to truth are we? The other says how close do we match each other, right? So when we're thinking about those two things in terms of GNSS, typically those things are the same, RMS and 1 sigma, if we have enough data, if we have good DOP values, right? So our geometry of our satellites is all quite good, and if we observe for a long enough period of time. All right, so just something to keep in mind when we're looking at these slides. When we're talking about the 68th percentile in my examples coming up, that's basically equivalent to RMS. All right, and here's a scatter plot. This is a horizontal scatter plot, multivariate statistics here that show the lat long of what it looks like when you take a whole bunch of GNSS observations of a point. Now you'll notice that there's some error ellipses being shown here. These are the 95th percentile error ellipses, so this is better than RMS. And in this case, we have RTK in red at 20 kilometers, so this is a differential-based rover, right? Then we have RTX in blue, and then we have, it's hard to see it right here, but in yellow is a VRS example with 17-kilometer baseline to our nearest physical base station, and then we have our site base in brown. So of course, this is where all of us want to be all the time, right? However, again, this takes time, right? Adds complexity to our workflows. So it might be something that we want to think about utilizing when it's necessary, right? When we're talking about these other solutions, I feel like we're all pretty comfortable with VRS. It's been around for a couple of decades. Now we have RTX available to us on these newer receivers. Something to be comfortable with as well. We're in the same error ellipse, right? They're substantially the same solution at this 2 centimeter mark. In addition, you will likely, since you now have RTX available on your receiver, you will likely start seeing these exfil modes. And I just want to make sure we understand what exfil means and how that works on a Trimble receiver. So exfil, if you haven't heard of this before, when you lose your correction source, right? So you lose either communication with your radio or you lose your cellular connectivity, so you can't talk across the internet, your receiver will switch into an exfil mode. And that is meant to fill in this gap you have in the communication, right? So exfil on normal Trimble receivers lasts for 5 minutes, right? And that 5 minutes is always included. But on your newer receivers that you bought since April, now that you have Centerpoint RTX also installed, you will get access to an additional mode, which is referred to as exfil X or exfil RTX. And this is an extended mode of exfil, so it will continue going beyond that 5 minute mark. And I think it's worth thinking about how this impacts us. Of course, where I live, plenty of cellular areas that cellular doesn't work very well, or you get a lot of dropouts. Certainly, if you're really stretching out those baseline lengths and you're starting to maybe get to the edge of where the built-in radios should be used, or maybe you're even pushing further with an external radio, and you start losing that communication, you're going to see these modes. And I just like everyone to kind of understand how these work. So I've got a couple of graphs. These plots are again showing multivariate 2D lat long, right? And there's a bunch of little lines that you see on here. The green line and blue is our position, of course, of the receiver. And then the red line, or the orange-red line, whatever this is at the top, that's our 68th percentile. So that's equivalent to our RMS values. And we step out, right, 95th, 99th percentile. And what happens in this case in the top is you can see that I was using a differential base rover solution, and this is a zero baseline. So I have one antenna, leads to a cable, there's a set of cable splitters, and I've got my two receivers, right? And one is acting as a base and one is acting as a rover. So all the variability or the error that we see in here is actually that first part, right? Remember, it's 1 centimeter plus 1 part per million. So that's that first part. That's in the antenna phase center and the latency of getting the correction information over to my rover receiver. So I then turn my internet off, and you can see that the variability increases. I'm switched into an exfil mode at this point. And what that is actually doing is it's using the Trimble RTX information for clocks and orbits, right? So we're limited. We only have clocks and orbits coming in. And so you can see these lines begin to spread apart pretty quickly. And so our engineers have said, okay, at about 5 minutes or so, we don't want folks to keep using this, because obviously if you're not accounting for the atmosphere over this period of time, the error is really kind of growing, right? So they turn it off and you switched into an autonomous mode. Now, once you have a Centerpoint RTX subscription, you also get access to this exfil X mode. And so here again, we see that I was doing differential base rover. I cut my internet off. The receiver immediately switches to an exfil mode. And you notice that the error estimates, precision error estimates, start to increase a little bit. And at that point, the receiver said, hey, wait a second, I can also make use of the atmospheric data that's coming from the RTX feed because I have a Centerpoint RTX subscription. And you'll notice that in this case, that RMS value, the 68th percentile, stayed nice and tight and stayed consistent much longer. And of course, this will just keep on going over to the right for as long as it needs to. So that's really how RTX works with exfil with your existing solutions. You make the switch into an exfil mode. If you have a Centerpoint license, you switch from exfil and then you go into the exfil RTX mode. So just something to keep in mind. Again, where I live, I'm way out in Pennsylvania. There's a lot of cellular dead spots. I run into this all the time. Folks who have AT&T here have a little bit better luck than folks that have Verizon, for instance. Where I used to live up in New York, it was the exact opposite. I had better Verizon service than I did AT&T. So again, practical consideration, you've got to have those same stations on the base that you have on the rover, right? And having multi-constellation, multi-frequency really does pay off. This isn't just some, sort of sales gimmick. Availability of satellite signals is crucial, right? If we want to cancel out or mitigate those biases, having the signals available to us is crucial. And in this case, what we're trying to show with this GIF is that even though there might be obstructions, right, even though portions of our sky are blocked, if we have multi-frequency, multi-constellation, there are so many other satellites that we still can maintain reasonably good geometry to those satellites and still have pretty good availability of signal. All right. Now, another practical consideration when you're talking about, again, RTX, those satellites are what we call geostationary satellites. So they're roughly down near the equator. This is the Indian Ocean satellite that we're showing as an example here. You notice that that satellite is pretty close to the equator. It makes this little tiny sort of figure 8 pattern to stay in position, and that changes its footprint on the ground as it moves around. So if you're in the northern hemisphere and you need to think about something that's at the equator, that's south of you. In the case of the US, the specific satellites for RTX are both to the southeast and there's backups to the southwest. So, you know, if you're thinking about, is there an obstruction? Is there some reason I can't get or see the RTX satellite? That could be why. You know, if you're in the southern hemisphere, you know, you'd have to look to your north and look for an obstruction. If it's being obstructed, you might have to think about switching over to cellular, right? So don't leave that as a tool that you don't have available to you. Especially important time, and I know we're starting to run out of time, so if everyone could hang out for a few more minutes, we'll get through the solar cycle stuff. Right now, we are heading into solar maximum. So our sun has poles just like our planet, right? Unlike our planet, these poles switch. All right, this happens every 11 years. The graph that it is showing here on the left-hand side of the screen, that's the they're actually measuring the magnetic field strength on the sun from a observatory that's out in California, Stanford University, and they can see this pattern repeat every 11 years. Now, we've been tracking this, scientists have been tracking this since the late 1700s, right? And each one of these solar maximums results in this activity that occurs because of that reversal of the poles. When there's higher activity, we see more sunspots out there on the sun. And that's what they've been counting since all the way back in the 1700s. Now, when there's more sunspots and there's more solar activity, that means there's more bad events that are happening, right? We're referred to as CMEs, or coronal mass ejections. These are highly charged particles that are hurtling towards our planet. They encounter the Earth's atmosphere and they wreak havoc on electrical things, right? And that includes GNSS, right? Because that's an electrical thing. So something to keep in mind, again, this has been going on forever and we are heading into a peak right now. By 2025, this should actually peak. And we should see it start to calm down again, and the interference that we're getting from the sun should begin to reduce. Why is this important to you, right? Well, there was actually a G4 event just last week, which is a pretty strong event, and back in May of this year, there was a G5, which is the strongest event. We were seeing outages all over the place during those G5 events, and we were seeing degradations to GNSS system performance under the G4 event. So these particles, they come to the Earth, they wreak havoc when they reach the magnetic field of the Earth. It disrupts electrical signals. So when we're thinking about you know, a approach that we might take, whether it's a differential-based rover or a modeled solution, we get different results, right? So in the middle here is a graph of the differential-based rover solution, and you can see in a ionospheric scintillation event, which is shown all the way to the right, you can see that there is a decrease in the precision of those measurements. So again, you get a change in the density of the atmosphere that's unaccounted for. That signal gets perturbed or gets the wavefront gets changed. By the time it reaches your receiver, it's really hard to actually be able to mitigate this. So in the case of here's an RTX solution all the way to the left, what we're seeing is that we were largely able to mitigate this event, right? Our errors were quite a bit smaller. And that's because we were using all those reference stations to create a model of the atmosphere versus depending on differencing those two things out like we would with a base rover solution, right? So very important and something that we should be thinking about, especially as we go into solar maximum. So in terms of practical considerations, that is certainly one of them. I go through, there's a blog here that's available to you if you'd like to check this out, that I wrote about all the real practical considerations you might want to make when you're thinking about your approach and which tool to use. This goes pretty deep into the topic. I just want to hit on a couple of the key ideas. The first one is, do I set up a base or not? So if we think back to our scatter plot with that very short baseline site base, we know we get good results. But the question is that always worth it, depending on what our task at hand is? Think about how long it takes you to set up a base. Think about at the end of the day, you got to tear it down, right? Radio, you got to set that up, you got to tear it down. Added complexities. And if you don't think about what that adds up to over the course of a year, I have a sample of that. So I use the New York State prevailing wage rate in this calculation. So that's $115 an hour right now. So that is the true cost of the employee, right? That is their hourly rate plus their supplemental plus their benefits. So true cost, if I think about how long those 10 or 15 minute tasks take me, if I do them every day, that adds up to over $50,000 a year. So when we're thinking about needing those really super accurate measurements, we have to balance that with what it's costing us to get there. If you can grab a subscription to your nearest VRS Now network, or you've got some free networks available to you, terrific different source of corrections to use that saves you this. RTX likewise, for the cost of an RTX subscription, it's substantially cheaper than $52,000 a year. So you can make sure that you do have not only that backup with the exfil extended modes, but you can also make sure that you could use RTX on its own and not have to go out there and set up a base. Likewise, for those of you who are doing Opus solutions, when you're thinking about doing Opus, here's another way to save money. When you go out and do Opus, they have recommendations, right, for how long you should occupy this point in order to get good results. And if you notice, to get down to 2 centimeters RMS horizontal, you need about an hour or so of data, right? Now, that's exactly where you would be at in mere seconds if you were using either RTX or your local real-time network, right? So if you put a nail in the ground, set up on top of it with your network rover, your RTX solution, record a bunch of epochs, you'll be at 2 centimeters or better in seconds. You don't have to record an hour of data. So this is something to keep in mind. Could be a great time saver for you. You'll be in the same ballpark in terms of the level of accuracy, right? So that's it. I know we're a few minutes over, but we will certainly hang out and take questions. If you are an existing, Trimble user, you've got a receiver out there, you made your purchase before the program where you were getting RTX included, you might want to give yourself a chance to check out RTX. And if you scan this QR code or you go to 30daytrial.trimble.com, you can fill out the form there with your receiver information, and you'll get a code emailed to you to check it out if you'd like. All right, Greg, anything from your side? Anything to add?
No, yeah, I check out the free RTX promo, and if you have any questions for us about putting RTX on one of the new receivers or setting it up in AAA Access, certainly give us a call. My email is right there on the screen. We did have 2 questions.
Okay.
So the first one, are we going to have slides and recording? Yes, those will be provided, emailed out after, I'm sure, a couple of days here. And then we had a question on the difference between RTX post-process and Opus. Are they calculating the post-process position with the same methods?
So that's kind of a nuanced question. So first off, if you're familiar with Opus, it does not have all this multi-constellation support, at least in the current release version of Opus. Now, exciting news for Opus users, they are actually adding multi-constellation support. So if you go to the Opus beta pages, you can use their new engine, which actually has multi-constellation. Now, RTX PP, of course, has multi-constellation because the RTX post-processing server is actually part of the Trimble RTX server. So there's a little bit of a difference there in terms of what signal availability there is. And there's also a little bit of a difference in terms of what the output is. So RTXPV, for instance, is outputting in an ITRF reference frame. So just something to keep in mind, you're getting some slightly different answers there. In terms of the mathematics behind it, I think you would find that those are quite similar, just noting the differences in constellation support, a little more complex mathematics. But yeah, I think you can get good solutions from either one. Just takes a little bit longer with Opus, of course. So it is kind of exciting that they're adding in multi-constellation support.
Okay. Yeah, we just had a couple more questions come in. First one, does the Trimble DA2 utilize precise point positioning? Therefore, it does not utilize base stations. I don't know if you want to go at that first.
No, feel
Jason.
free. Yeah.
Oh,
I mean, if you want me to do it, you
can correct me if I'm wrong on something here. So, I mean, the DA2 functions just like, when any R12 or R980 would. They actually do use the for some reason the term is escaping me at the moment.
A correction sub or catalyst. Yep.
Yeah. So I mean, like with the DA2, yes, you can use RTX, you can use WIS cores or VRS now. So yeah, I guess to answer the question, yes, it does, and then it also uses any other correction method, like any other rover would. It's a little harder to get a UHF signal into it, but it can be done in Access with some extra equipment. So.
Yeah, and I guess the only other thing I would point out about the DA2 in comparison to some of the other receivers, like the R12, the R980, 750, et cetera, that we showed on the earlier slides, just keep in mind signal support matters, right? So having that multi-constellation, multi-frequency is important to get really terrific results and make yourself more resilient to things like solar cycle 25, more resilient to multipath and things of that nature. So the DA2 doesn't quite have all the signals that the other ones have. So if you know you're going to be in some compromised environments, again, it's something to think about when you're making an investment in equipment.
Yeah, and ProPoint was the technology I was thinking of. And then one more question that came in: can RTX be used for Esri field map corrections through the Trimble Mobile Manager app?
I believe so.
Yeah.
I don't think there should be a problem there. You could set it up with TMM. It's going to just stream you a position out, and you're going to take that right into your Esri product. I think the trouble with sometimes with like a NEMA outsource or something like that, going to some of these third-party the softwares is that you don't necessarily get all the advantage of the let's call it the Trimble solution, where it's built in, right? So some things can get lost in NEMA because they're proprietary, right? Therefore, they're not in, let's call it the NEMA standard. And so not all softwares can ingest the information that Trimble is putting into NEMA, let's say, equally.
Well, I don't see any more questions. Again, you can feel free to email us or Seiler in general. But thank you, Jay. Oh, one more. Okay, well, that's actually from one of our people. Yes, Field Maps is compatible with RTX. So, okay. But yes, well, thank you, Jason. Thank you for giving us a ton of information today. Again, go sign up for the RTX demos or contact us if you need assistance with helping with setting up something on your new receiver. So, but thank you again, Jason.
Yeah, thank you. Thanks for having me, Greg, and thanks to everyone out there for their time today. I really appreciate it.